The last video we were looking at some of the properties of Fourier transform. One of the property that we had yesterday is in the last video is this when f and g both piecewise smooth functions, periodic functions with period L, and if you consider the product of these two functions f into g, Fourier transform of product of these functions, which is given as a convolution sum, that sum from f cap of k into g cap of n minus k. So, in the proof of this property we have used what we have done is the integral, we just we pass the integral inside the infinite sum. So, that is not legitimate in general unless that series, the sigma k is from minus infinity to infinity, whatever that series function of k, that series should be uniformly converging. So, we have defined what is, I will just now in this video we will have we will just define what is the uniform convergence again. We will just look into the uniform convergence and under what conditions the Fourier series is actually uniformly convergent. So, after proving this, so it so happened that when f is f and g are piecewise smooth periodic functions, this product is also piecewise smooth periodic function, that implies its Fourier series actually uniformly convergent. So, we will prove this result using, for that you need just a small result. One is the Weierstrass M test and uniform convergence. Anyway, we will just prove, we will just define what is uniform convergence. I will explain what is uniform convergence, and also I will just state what is M test. You just need these results always, these are actually coming from calculus, and then once you have this you need a Cauchy-Schwartz inequality for the sequences, that is basically series. I will just give you some inequality. Using that one can prove that if f is a piecewise differentiable actually piecewise smooth, that means what you need is f dash is piecewise differentiable function. If such is the case for f, the derivative is piecewise smooth piecewise differentiable function, that means two derivatives, second derivative. So, d square f by dx square, this should exist as a piecewise continuous function, then you have the Fourier series converges. You can prove that the Fourier series of this function f x is uniformly convergent, uniformly and absolutely convergent. So, this is what we will see. For that I will just state start with what is a uniform convergence. So, we will digress here with the uniform convergence. So, let us see what is a uniform convergence. So, before you know about this uniform convergence, what is the convergence of a sequence of functions? So, if you consider a sequence of functions f n of x, this is a sequence. So, it is defined for every n 1, 2, 3 and so on. For example, you have sequence of functions and x belongs to, let us say, some a b, it is defined over a closed interval a b, and you say that f n of x converges to f of x pointwise convergence, converges this means converges to f x. We say that f n converges to f x pointwise if f n of x limit of f n of x as n goes to infinity. So, you just write here converges is equal to f of x for each fixed x in a b. What is the meaning of this? This means f n of x minus, you fix x and this difference, this is a given epsilon positive. So, you give any epsilon positive, you get what you get is this will be less than. So, this quantity is less than epsilon. So, whenever you have n is bigger than capital N for some n. So, give epsilon, there is a n, for some I will write for some n belongs to natural numbers. Okay. So, this n give epsilon, there is a n. So, such that for every n bigger than or equal to n or bigger than also n, this is also okay. Okay. So, let us use n greater than or equal to n depending on epsilon here, because you fixed x. Okay. So, for every x you have, and once you fix x, so that is also depending on. So, the moment you fix your x and you fix your epsilon, there is a n. So, basically it depends both on this number n that belongs to the natural numbers, that depends both on epsilon and x. Okay. Then you say that this converges pointwise, and suppose you have for each n, for each x in a b. Okay. Suppose you have this n for each n and a fixed epsilon, let us say epsilon is fixed, given epsilon, you fix epsilon, the moment you give epsilon fixed. Now, for each x you have this epsilon x, then you consider the supremum of all this, x belongs to a b. So, that means basically maximum of them. Something is supremum means something, so this is the set, for example this is the set, this is the supremum means which is always bigger than, so or kind of maximum. Okay. So, this is the maximum. So, because it is a maximum, supremum or maximum, because it is a closed and bounded set. So, you can see that this is a maximum. For a continuous function, if it is a continuous function on a closed and bounded, is the maximum always exists, but let us otherwise you say supremum. Supremum is always, so the some number, this means some number that is always bigger than the set. Okay. So, that means n epsilon x belongs to, when x is running over this closed interval, and you consider that set there is a number which is called the supremum of all these, which is bigger than or equal to all these numbers. Okay. Supremum, if its supremum is finite, okay, then you call this n naught is this supremum. Then what happens? Fn of x minus fx is less than epsilon if n is bigger than this n naught. Okay. And this is true for every x in AB, right. If such a supremum exists, then you say that then this n is no more depending on x. So, this n naught is actually depending only on epsilon now. So, let us write this n naught only depends on epsilon. So, so the moment given epsilon, so given epsilon positive, if you have this difference is less than epsilon, if for every n bigger than or equal to some number that depends only on epsilon, but works for every x whatever you choose, then you say that Fn of x converges to Fx uniformly. Okay. So, for example, I just give you some example. Fn of x, if I define x power n, x belongs to open 0 1, okay, and then otherwise okay, closed 0 and open. So, otherwise it is 1, x equal to 1, let us say. So, if you define like this, and what happens to this function Fn of x? Fn of x, you fix x within here, Fn of x is x power n, because x is less than or equal to, if x equal to 0, this is anyway 0. So, this goes to 0 if x equal to 0. If x is between 0 to 1, if it is 0 to 1, this is always, because this is 1 by, so this is less than 1, x power n is actually, as n goes to infinity, because this is x is less than 1, this is going to 0, okay, if x belongs to the open 0 1, and if this converges to 1 if x equal to 1, because once you put x equal to 1, Fn of 1 is always 1. So, that converges to a constant function which is 1 for as n goes to infinity. That is the meaning. So, is this converging pointwise? Yes, but you fix for every x value is going to some number. is 0 for once you if you are here this is converging to 0, if x equal to 1 it converges to 1. So, it is pointwise convergence is true. This is a pointwise convergence, this is what is true for this example. Okay. Whether it is uniformly convergent, that is what we have to see. So, that is how do you see that this is actually not true. I will just graphically show you. So, once you have this x power n between 0 to 1, this is 0 to 1, f1 looks like at 1 is 1, this is 1. So, this is 0 to 1. So, this is x axis and this is y axis, and at x equal to 1 this is always 1, and as x goes to as between so this is at x equal to 0 this is always 0, okay, at x equal to 0, and as x goes to, so for every, so f1, let us consider f1 is a function which is converging to, which is like looks like this, let us say x equal to 1, x equal to 1 basically it is a linear function. So, it is like this, x square, so it is like this, okay, x cube will go on like this and so on, x as x power n goes, finally you end up going like this as x. So, this is your f1, f2, f3, f4 and so on, that is what happens. Okay. So, you see f1, so you fix 1 here. So, 1 at every point if you fix x value is finally converging to 0, it is converging to 0 0 0 even at including at x equal to 1 the value is always 1. So, it is 1. Okay. So, at 1 the always function value is always 1 for all n. So, it converges to 1. So, pointwise convergence is there. So, what is that why is it not converging uniformly? Because you see that there is no n. So, if you fix your x here, if you fix your x, there is some n beyond which this is always less than this quantity f n x minus f x. So, you can see that f n of x, if you want that for every x, and what is f n of x? It converges to the f x which is 0 0 if x is 0 to 1 and 1 if x equal to 1. So, such a function it is converging pointwise. So, what happens when you take the difference f n x minus f x, this quantity is always less than f n x for whenever you are here is always less than so as this quantity is going to 0. So, this is how shall I say you see to tell graphically speed with which this is converging to 0. So, you fix x value speed it converges to 0, and you fix any x value speed at which it is converging to 0. So, if it that is among all the speed at which it is converging to 0, and this should have minimum speed among all of them, that should be valid. If you have such a minimum speed, least speed that works for all convergence. Suppose you fix x1, x2 and x3, okay, the speed at which this converges to, if you are at x1 fn x1 converges to f at x1, you will find the speed of convergence. If the way the speed it converges, the speed converges here and the speed converges here. If you look at like that everywhere, if you have the least speed of convergence, so with that least speed it works for every that is the minimum speed. So, you should have a minimum speed for all points. So, that if there is a minimum speed that works for at every point, that means there is a n. So, then you have a uniform convergence. So, there is a convergence with that speed for at every point. So, basically that means you have a uniform convergence. So, roughly you can say like that. So, mathematically it says that you see you have some n that works, that depends only on epsilon, okay, and but not does not depend on the domain x value. So you can just look into some calculus books, what is the uniform convergence, you can get this. So if you have a uniform convergence, such a uniform convergent sequence of functions, what happens? A limit fn of x as n goes to infinity equal to fx uniformly. If you have such thing, I can differentiate term by term, fn dash of x equal to fx, okay, uniformly in x in AB. Suppose you have this, and you can do term by term integration. So the derivatives limit also goes to that one, and you can also x belongs to AB. So derivatives means is defined only in the open interval. So this is this, and you can also integrate from a to b fn of x dx. This limit n goes to infinity, this is same as integral a to b. You can take this limit inside fn of x dx as n goes to infinity. So this is nothing but a to b fx dx. So if this is the case, if it converges uniformly, then we have roughly these results. This is 1 and this is 2. You can do term by term, you can do differentiation. In the derivatives, you can pass the limit inside. Okay. This is basically what happens. I can pass this limit inside the derivative. This is d dx. I can pass this limit inside the derivative. So that means this is d dx of this. This we already know that this is fx. So d dx of fx is f dash. So when I have d dx here, this will be simply f dash. Once I pass this limit inside, that becomes d dx of limit of fn of x, that is limit of fn of x is fx, that is exactly this one. So whatever I am doing here, I am passing this limit inside this integral, here I am passing this limit inside d dx derivative. So these two results are true whenever you have uniform convergence. So there is the sufficient conditions under which you can do these operations. And what is its relevance here? In the property 5, if you see property 5, when you are given two piecewise periodic functions with period L, you want to show this result. So when you do this somewhere here in this, I allowed this integral, I pass this integral inside this summation. So far we have done, so I will just do the analogically what is this. So if this is uniform convergence, analog is the equivalent things also you can put it. So if you have uniform converging, so you can also see this series of functions. For example, if you look at the series of functions, n is from 1 to infinity, you can view this as this series. Okay, this is this, if you call it fx, this you can view it as Sn of x, which is partial sums. N is from 1 to or rather k is from 1 to n f k of x. So you consider this as Sn. This converges to, as n goes to infinity, this converges to fx, right. It's clearly as n goes to infinity, this certainly is converges to fx, because this sum is this. If this converges to uniformly in x belongs to AB, then you apply those results. So you can write Sn dash of x is f dash of x. What is that Sn dash? Sn dash converges to f dash of x. What is Sn dash? That is simply k equal to 1 to n f k d dx of this of f k of x. This converges to, what happens to this? So once basically you can pass this limit inside. Okay. So basically you can pass this Sn d dx of Sn, that is f k dash. So that is finally becomes f dash of x. Okay. So if you say f dash of x is simply f n dash of x, n is from k is from, or n is from 1 to infinity. If this is your f dash of x, this converges to f dash of x. So this so you can view this as a sequence of partial sums, then apply these results. Now you have a sequence that converges to a sum. And similarly, and this is one result, and the second result is you can integrate term by term. So, integral Sn of x a to b dx is same as this converges to integral. So, here I have a limit outside, I pass it on, that is going to be Sx. So, limit Sn x as n goes to infinity, that is Fx a to b dx. So, the same thing. So, you get, so this what does it mean? So, this means this sigma n is from 1 to infinity, sorry, n to k is from 1 to n, f k of x, this is my Sn of k, Sn of x. Now, I have this for this integration a to b, I have this limit n goes to infinity. This is, now I can pass this limit inside this integral, because this is uniform convergence. A to b sigma k is from 1 to n f n of x as a limit inside now dx. This is same as a to b, this is going to be k is from 1 to infinity, and once I pass this limit, this is f k of x dx. So, what is this one inside is nothing but a to b f x dx, that is the sum. Okay. So, you could pass this inside limit and you end up, what exactly is this? Is this one. So, you pass this one. So, both are possible. So, either you look at series of functions or a sequence of functions. Series of function is equivalently, you can put it as a sequence of partial sums. So, once you have the uniform convergence, if you assume the uniform convergence, and you can do these two operations. So, that is what we do. So, once f is if f is piecewise smooth periodic function, that means f dash is piecewise differentiable, and also f double dash is also piecewise differentiable, or any nth derivative is piecewise differentiable function. In that case, you call this piecewise smooth function. F is piecewise smooth function if any derivative is also piecewise differentiable function. In that case, we can pass this limit. One can show that the partial the series, the Fourier series is actually converging uniformly and absolutely. So, basically we use this uniform convergence. So, to show this uniform convergence, so we will just see this one. So, if f of x is just write it as a result. So, if f of x is a piecewise smooth function, smooth periodic function with period L, then what you have is its Fourier series. Obviously, once it is piecewise differentiable, it has a Fourier series, that is Cn e power minus I or plus I. So, I n omega naught x, n is from minus infinity to infinity. So, this series converges uniformly and absolutely as well. So, absolutely means some series sigma f n of x converges, n is from minus infinity to infinity, converges absolutely if, when do you say this is absolutely? If mod f n of x converges, n is from minus infinity to infinity. If this is the case, if this is converges to some number, okay. If this converges pointwise, if you say only pointwise, then you say that is absolutely convergent. If fix x and you take the modulus value, if it converges, you say that is absolutely converges. So, this is extra. So, this is absolutely convergence is also true. So, to prove this one we need, so this is basically we use the M test. Okay. So, what we use is to show this, to show that this is true, what we need is we use M test. If you have M test is M test, Weierstrass M test, that tells you that you have two series f n of x. You want to know whether this series is uniformly convergent or not. You want to see this uniform convergence, converges uniformly and absolutely if mod f n of x. So, if you can take the modulus of this is bounded with some numbers, let us call this some a n's, they are bounded and sigma a n is from 0 to infinity or minus infinity also you can take, okay, and this is bounded. If once this is true, so you have a bound for every f n. So, this is true for every n, for each n, okay. If this is true for each n you have some number a n which is bound for that function, and then and you have this those numbers, this number series is finite, then this converges uniformly and absolutely, that is what is the M test. So, we use directly this, this is a very important result in the calculus. So, we will try to apply this to this Fourier series. What happens when do you, so you have this, you want to show that this series is Fourier series is uniformly convergent or absolutely convergent. So, absolute convergence, if you see what is that absolute convergence, you take the modulus of this, that is only simply mod C n, okay. Absolute convergence if this is finite, period, okay. So, if this is true, this is absolute convergence. Uniform convergence by this M test if at least this is a sufficient condition, if and you see this this term is bounded with, this is modulus of that is C n, mod C n. So, you have this C n e power I n omega naught x, this modulus is obviously less than or equal to modulus of C n for each n, and if sigma C n is from minus infinity to infinity, if this is bounded, okay. Okay. So, so uniform convergence is of this Fourier series is guaranteed. Where is the Fourier series? Here. So, this series is guaranteed, uniform convergence of this Fourier series is guaranteed once you have this is each of the terms are bounded with this Cn's that is known, and that is no, right, this is modulus of this exponential function e power I n omega naught is 1. So, this is this, and if I know that this quantity, if this is true, then from the M test I can say that this is uniformly and absolute convergence, okay. Then I can simply pass the limit. So, I can integration here is same as this is equivalent to summation, I can take this integral inside, okay. That is what I will do. Then you can get the, you can justify the property that I have proved in the last video, fifth property that I have proved in the last video. So, to show this this one, so given a Fourier series sigma C n e power I n omega naught x, if that series is uniform convergence, you need sigma mod C n should be finite. So, this is actually true if f is a piecewise smooth function, okay. If f is a piecewise smooth function, this is always true. For this we need Cauchy-Schwartz inequality, Cauchy-Schwartz inequality, okay. So, what is this one? So, you start with simple, you take two real numbers, you call this x and y. If you take the difference between x and y, let x and y belongs to real numbers, two real numbers you take the difference and square it, what is its value? Is always positive or 0. So, if you expand this, x square plus y square minus 2xy is greater than or equal to 0. So, this means x square plus y square is greater than or equal to 2xy. So, what does it mean? So, this is always will give me xy is less than or equal to x square by 2 plus y square by 2. So, this is the starting point to show this Schwarz inequality that we will show for the sequences. So, Schwarz inequality tells you, I will just write directly. So, if you have a 2 series, if sigma a n square n is from 1 to infinity, if this is finite, okay, let us say mod. So, they are all positive numbers, so that I do not put the modulus, and sigma b n square n is from 1 to infinity, let us say and this big b n square, these are number, this is also finite, then sigma a n b n. Okay, so if you have, we can also keep the modulus square if you want. So, they can be even complex numbers. So, this modulus of a n, modulus of b n, both together, n is from 1 to infinity. This is, question is whether this is finite. Okay, is in fact, if these are finite, this should be finite because of this inequality. Sigma mod a n square n is from 1 to infinity, you have this with root, and sigma b n modulus square n is from 1 to infinity, for this again on half, because these two are finite, these two are finite. So, obviously this is finite. So, that is what is actually this Cauchy-Schwartz inequality tells you. So, we will prove that. So, that this using this we will try to show that this is finite. Okay. This the sigma mod c n is finite. So, to show this Schwarz inequality, we will try to start, we started with 2 real numbers, and the difference is always square of the difference is always greater than or equal to 0, and that gives you this inequality. Now, next step is I consider simply I take x equal to mod a n and y equal to mod b n. Okay. Let us take this, then what happens? Mod a n mod b n is less than or equal to mod a n square by 2 plus mod b n square by 2. This is true for every n, right. So, you can just add them up. If you have inequality that is true for every n, you can sum it up also, n is from 1 to infinity. Then you have sum is from n is from 1 to infinity, sum is from n to 1 to infinity. Okay. That is what you have. Okay. So, here we have we assume that, so these are the numbers, they are all finite, they are all real numbers, and they are real numbers, they are all finite. So, because they are finite, already we know that their sum is finite. So, given that their sum is finite, you can sum them up, a n plus b n. This series, this sum, once you know that this is finite, I can see that this I can write like a n plus sigma b n. If they are finite, this whole thing I can sum the way I like. Once, or in other words, once you know that a converging sum, a finite sum a n, n is from 1 to infinity. If this infinite sum is finite, if this is the case, I can sum it. This is actually a 1 plus a 2 and so on. I can also add, I can rearrange these terms and then add it. Okay. I can do a 1 plus a 3 and so on first, and then plus a 2 plus a 4 and so on. So, these two sum together will be same as this one if this is finite, okay, and they are positive numbers. This should be a n's are positive. If a n's are positive and this sum is finite, this is what I can do always. So, if I use that, that is what I can do. So, once I sum it up, what you have is summation is actually a1 plus b1 plus a2 plus b2 and so on, like that. So, now I rearrange such that a's I put it together and b's I can put it together on the right hand side. This is what is the result. Okay. Now, next step is I consider, I simply, instead of choosing this, I choose because this sum is finite, sigma a n mod square, n is from 1 to infinity. This is here also I divide with n is from 1 to infinity mod a n square. assume that is positives, okay, because it is positive and it should be non-zero. Okay. If I choose this one, again like earlier, if you substitute, so instead of simply taking this, if you substitute, so instead of x, instead of a n, I will replace this term, right. I can simply, I have chosen y n b n like this and then I summed it up. Now instead of a n, I can choose a n divided by sigma a n. Okay. So if you do this, n is from 1 to infinity, instead of a n, I can also choose a n, or rather start now itself you can do. So this divided by some number s, some number s. So what happens? You have s square and you have here, what do you get? So you have s square, right, s square and s square. No, let us is not the way to say. So so we have chosen x equal to this, y equal to this, and you add it up, you get this one. This is what you get. Okay. Now instead of choosing this, you can also replace a n's by mod a n's by mod a n divided by sigma a n mod square. N is from 1 to infinity. So you choose, instead of a n, you choose this quantity. So here itself, when you x equal to, you can choose this by this quantity. Okay. So let me put it that way. So let us start with that. So let us choose x equal to this divided by sigma mod a n square, n is from 1 to infinity, and y equal to mod b n divided by sigma mod b n square, n is from 1 to infinity. Then what happens? A n b n divided by sigma n is from 1 to infinity mod a n square into sigma b n mod square, n is from 1 to infinity. This is less than or equal to x square is a n square by sigma a n square, n is from 1 to infinity, okay, of this square by 2 plus by 2 sigma b n square by sigma mod b n square, n is from 1 to infinity, this whole square. So this is what is true for every n. Now you can sum it up both sides to see that sigma a n b n, n is from 1 to infinity, and you can see that divide by sigma a n square. This is a number, fixed number, 1 to infinity, sigma mod b n square, n is from 1 to infinity. This one is less than or equal to, now you have this sigma. So sigma mod a n square divided by n is from 1 to infinity. This is a number, fixed number. So this is like with 2, 1 by 2, this whole thing comes out, that is 1 by mod a n square whole square, okay, plus 1 by 2, this sigma n is from 1 to infinity mod b n square whole square. Now here I get, because I summed up over n, this b n square, n is from 1 to infinity. Okay. Now what? So you can cancel this, this gets cancelled. Okay. So this quantity is less than, strictly less than 1 by 2, because this is 1 by some positive quantity which is less than 1, and this plus another half. This is also 1 divided by the sigma mod b n square is always less than 1, okay, because they are all positive quantity. To avoid this, you do not want this inequality here, what you can do is, instead of choosing x equal to this, here you choose this with root. If you choose with root, what happens? So you have this with root, you have this with root, and here there is no squares, okay, because square root, once you square it, this is going to be without that. So that what you have is that you do not have this one, you do not have this, and now this completely cancels. So what is left with is half plus half, which is 1. So this is with half, with half. So this implies sigma mod a n b n, this product is less than or equal to sigma n is from 1 to infinity a n square into sigma b n square, n is from 1 to infinity with square roots. So this is your, this is exactly your Cauchy-Schwartz inequality, that is what we have proved. So how do we show that the sigma c n is finite? Sigma c n is finite. Now we have to show this one. Okay, if c n is the Fourier coefficient of function f, that is piecewise smooth function. If it is piecewise smooth function, why is it so? So we will start with so we will show that this is this, n is from 1 to infinity, or rather you have minus infinity infinity. So this mod c n is actually equal to c 0, 0 term I put it outside, mod c 0 plus n is from minus infinity infinity, n is not equal to 0, and what you have is this c n, right. So if, because it is piecewise differentiable function, and you have seen that f dash, if f is piecewise differentiable function, f dash of x exists. Okay, f dash of x is a piecewise continuous function, piecewise continuous function. But now we are seeing that if it is a piecewise smooth function, f double dash of x exists, and f double dash of x is actually piecewise continuous function. That means f dash of x is piecewise differentiable function, implies it has a Fourier series, and once it has a Fourier series, what we have seen is f dash x is sigma, so it has some Fourier series, n is from minus infinity infinity, and dn into e power I n omega naught x, that is this Fourier series, and we have actually seen that dn's are in terms of f, that is I n w naught, cn will be dn, cn, okay, dn will be cn. So this is equal to this e power I n omega naught x, that is my f dash of x. So so because dn equal to this, okay, so what is your cn? Cn's I can write, cn's I can write. So from this I can write cn as dn divided by I n omega naught. So mod cn will be mod dn. So this is mod dn divided by my is 1, so mod n. So this is n mod omega naught. So n into omega naught 2 pi by l. This is a constant. Okay. So this is 2 pi. So mod omega naught, that is anyway constant 2 pi by l. So you can write like this. So this is c 0 plus sigma n is from minus infinity infinity, n is not equal to 0. Now we have this this comes out 1 divided by mod w naught, that is a constant comes out, mod dn divided by n. Okay. And since f is a piecewise f dash is piecewise differentiable function, and it is integral square integrable function, f dash square minus L by 2 to L by 2 is finite. Once it is finite, by Bessel's inequality you have this sigma dn, so Fourier coefficients dn square, right. So this dn square, n is from 1 to infinity, this is also finite by Bessel's inequality. Just see earlier videos, Bessel inequality, if we know that f dash is a piecewise differentiable function, it has a Fourier series, and because piecewise differentiable function, it is also integrable, it is a square integrable function, it is integrable function, implies absolutely integrable, implies it is also, because it is over a finite domain, it is also square integrable function. So because of this, now because this is finite, by Bessel inequality this quantity is finite. Now you apply Cauchy-Schwartz inequality for this. So you get mod c naught plus 1 by mod omega naught. Now this is less than or equal to if I apply this Cauchy-Schwartz inequality, n is from minus infinity to infinity, n is not equal to 0, and what you have is this is a n is 1 by n, b n is mod d n. So, what is this one? So, a n square sigma a n square, that is 1 by n square into this half into sigma n is from minus infinity to infinity, n is not equal to 0, mod d n square. So, you see that mod d n square, this is always finite, okay, by Bessel inequality, because f dash is integrable, f dash square is integrable. So, this quantity is finite and we know that this is finite, sigma 1 by n square is always finite, this is 2 times n is from 1 to infinity, this quantity is finite, this is by calculus. So, overall this is finite, this C0 is anyway constant, that is a finite, W naught is constant. So, we have shown that this quantity is finite. Once this is finite, by uniform convergence, this is true and this is always true. So, this means uniform convergence. Because of this is true, that is same as this, so absolute convergence is also true. So, you have your Fourier series, once f of your function, your signal is piecewise smooth periodic function, you have the Fourier series is uniformly and absolutely convergence. Okay. Now, let me go back here to that property 5 that I have proved yesterday. Now, what I have is these are the two functions f and g be two piecewise smooth functions with period L, and I consider this product. This product if I consider, then you have to show this is the one, and what I choose is the left hand side. I started with the definition of this Fourier transform of the product of functions f and g, and you have you introduce, because f is a piecewise smooth function, you can write f as a Fourier series. I put this Fourier series, and now I take this integral inside, because this Fourier series f cap of k, that is your Cn, into e power I k w naught, and you can also include this one inside. Okay. So, only k, so k inside this k integral only you are introducing, and you are passing the integral inside. So, if you look at this one, this is since this series is uniformly convergent, you can pass this limit inside. Okay. So, that is what you have done here. So, now this is legitimate, and once you pass the limit, this is exactly nothing but the Fourier transform of g dash at n minus k. So, this is exactly what we want, the right hand side. So, it is completely justified, the property 5 is proved. So, for that you have to use this uniform convergence and Cauchy-Schwartz inequality. It is a part of calculus that I have done here, just to recall. So, I try to use minimal things to prove this, and then prove the property 5. So, this is how we can show this property 5, and then maybe next video we will try to do some examples, maybe one or two examples. We will try to we will have a recap of what we have done so far for the Fourier series, all the results that elementary results that we proved, minimal results we try to prove. Okay. When we choose the signal, what kind of signal is, what kind of function it is, whether it is always, once you give the signal, mostly it is a piecewise smooth function. Once you have, so once it is a piecewise smooth function, what are all the results we have mathematically, how to calculate this Fourier transform, and also some results on delta function that we may need further in the later videos, that we will try to do in the next video and finish the Fourier series part. Thank you very much.